Okay, very good. Is it recording? Alright, let's begin. I'm going for the checker start. Today we'll talk about a new topic. So last time one of you asked me, last time we saw like the state-of-the-art self-supervised way to learn visual representations from images. And somebody asked me, do we really need to have this pipeline of augmentations? Do we still need to rely on image augmentations? And I said yes, as long as you do this type of discriminative type learning, where we take an image, we take two views, we process them either with the same network. It's called either CMEs network when the networks have the exact same parameters, or with this teacher-student dynamic, where student is updated through backpropagation, the teacher is updated as an exponential moving average over the parameters of the student. So in this type of visual representation learning, you do need the augmentations. However, we can borrow some ideas from the field and the progress in the advancements in natural language processing and try to come up with different strategies to incorporate masking. So masking is the alternative to get away from the image augmentations. So we saw that when I refer to image augmentations, I refer to random precise crops of different scale, usually from 5% to 100% of the image, or color jittering, which is basically distorting the statistics of brightness and contrast of an image. And additionally, for natural images, you can distort the saturation, and you have these parameters where you can control how much you want to distort those statistics. Okay, so we saw DINO. So here, this is what I mean by discriminative way of learning representations. So we want to match in some feature space, either if it's softmax and we need to assign classes, or if it's directly on the feature space, as we showed this other method called BEiT, where you try to directly minimize the mean square error between the two networks. So let's see how we can go one step further and stop relying on augmentation. What are the resulted augmentations, what are the resulted representations that we do learn from this kind of methods? So we'll start with the first method. It's called MAE, is the abbreviation, or masked autoencoder. So this is a quite simple method. So if you remember from the first 2 weeks, we saw this idea of autoencoders. So we have like any type of network that is decomposed in two networks, so the encoder and the decoder. This is generally for autoencoders. So you have the input, you apply some perturbation on the input, like Gaussian noise, masking, or something like that. Then you have like a vision transformer or a convolutional neural network where you have some compressed version of the input and you have some representations. And then the decoder network is responsible to move back from the continuous feature space, or latent space as it's called, because it's kind of hidden, because the network is not really directly optimized on the latent space. And the second network is called the decoder, which in practice you can imagine this with transposed convolution or convolutions plus upsampling. The bottom line is that you need to move back on the initial image space and then calculate the loss on the initial image space based on the undistorted image. So this is the first approach that showed that we can learn representations by directly mimicking the pixel intensities, so directly on the image space, as we can say. So what is so special about this method? What is really, really attractive is the part that we can combine this idea with vision transformers. So the vision transformers process a sequence as a set, as we have discussed already on the course. And the big advantage is that if you consider, if you treat the images as a sequence, you can discard tokens or elements of the sequence, and you don't need to process them on the encoder network. So the image behind me, you see that the encoder network is not processing the masked patches that are indicated with gray little squares. So the more I mask patches on the image, the more computational complexity I save, because I don't have to process this on the encoder network. Is that clear? So in the case of, if I mask 99% of those patches, in the extreme case I only have to process 1% of the unmasked patches. And this is the first work that kind of created this trade-off, which gives you a lot of computation. And the main reasons that they aimed for such an approach is that this makes things even more scalable. So you can imagine also, you see the two networks are asymmetrical, meaning that the encoder has a significantly increased number of parameters compared to the decoder network. So these are just two vision transformers. So you cannot have the same method with a convolutional neural network, because you would need grid structure data. So you cannot remove those masked patches, as we saw some approaches from 2016 and 2017 where they tried to do something similar with in-painting with convolutional networks. They didn't have this advantage of being able to discard and not process this information on the encoder. So the trick is that you cannot completely avoid these unmasked patches, you still need to add them, but you have the decoder which is responsible for reconstructing basically all those tokens or projected patches back to the image space. So you don't just blindly mask the patches, you need to remember which positions you have, which positions in the sequence you have masked, and then you replace them. So you see the number of input and output tokens of the transformer is always the same. But then you have the additional step that you need to add back in the correct positions the masked tokens. So you can imagine this is like similar to the CLS token or the end of, it's like a trainable token, but in its layer of the decoder, of the transformer of the decoder. This after processing the blue, which is the representation from the encoder, and the masked token, you will have a different representation here as indicated with the red little squares. Is that clear? How do we win? Okay. So then I need to ask a very important question. What is the masking ratio that it would be, let's say, the optimal? What would be the intuition on how to pick the masking ratio? How much of the patches should they mask? So let's go back to, because as I said, these methods are built upon the improvements on natural language. So there is a lot of analogies and correspondences that we have to think as to how we could process signals. So both signals both images and natural language can be regarded as different type of signals with different particularities, all right? So let's go back to the BERT approach. Does anybody remember the masking ratio if you want to train a BERT model in natural language? Approximately? No? Yes? Yeah, 15%. So in natural language, when you have a sequence, okay, do you also remember what are the tokens in natural language? What do they represent? What information do we represent with one element in the sequence?
An embedding of a word.
Sorry, what?
An embedding of a word?
Yes, so these are word embeddings. So this is word 1, word 2, word 3, word 4, word 5. So we take a sentence. Let's ignore the start of sentence and end of sentence, because now we're trying to establish some intuition. We don't care so much about the technical details. So today is a great day. We map all those vectors into the vocabulary and project them, and we end up with word embeddings, and we can have as many word embeddings as the vocabulary of a language. And then we mask 15% of them, and we replace this with the masking token, which is basically a vector that will be trained alongside the network. And after the processing, we try to predict word 3, so the word, so the entry of the vocabulary. So if the vocabulary is the number of classes, so it's a kind of supervised problem where you have cross entropy, even though we call it masked language modeling. In the end, it's just cross entropy, and we are trying to predict the entry, the index that correspond to this word embedding. Any questions? Okay, so if we can regard two types of signals, what is the fundamental difference between words or sentences and an image as a signal? Any intuition? Yes?
An image has a fixed size.
Yes, we have the grid. It's structured in a grid. Okay,
and also the vocabulary. Let's say vocabulary here is kind of also fixed. Like we have channels with like.
The vocabulary in natural language, you mean like you have like a specific set of words?
In natural language, it's a set of words. In computer vision on images, it's a limited like range of values, I'd say.
Range of values. Can you be more specific?
In terms of like if you're talking about pixels, so you have specific.
You mean we have intensities? Yes.
Intensities, yeah.
So I would say in NLP we use word embeddings, in computer vision we use directly the data, and computer vision is more like continuous data, where NLP is more discrete.
You mean that the pixel intensities have a continuous range, in general it could be something from 0 to 255. Yeah, that's partially true. So let's stay on the grid structure. So you all agree that we have some grid here. So the data is structured in the grid. And what is the intuition that we use the inductive biases of convolutional neural networks? What is this? This particularity of images as signals that we try to leverage with convolutional neural networks. Yes?
Let's say in images, the inductive bias is that like the information is distributed like spatially.
Yes, this is equivalent to say that it's structured on the grid. So spatially it's the grid. It's either 1, 2, or 3 degree. Okay, but what is happening here? What is the, how can I say without giving you the answer? What is the intuition that we use these convolutional neural networks and we group these pixels together. Yes?
Pixel values influence the other values locally around it.
Okay, yes. Influence is a different answer. Okay. So let's say we have 3 different dimensions. Okay, 2 different dimensions. This is an image of 224 by 224. And then, let's say I want to downscale the image. So I only keep from each neighborhood one of the pixels. So I take small regions and I resize the image to 32 by 32. So I downscale the image by a significant factor. Can we still see, as humans, can we still see what's happening here? When we go from a small image, when we downscale the image, like the images you had in the exercise, like this STL10, Cypher10, all these data sets. Can you still visually identify the information? So by reducing the information of a factor of, I don't know, 224 divided by 32? What?
7.
7? Yeah, okay, thanks. So by reducing the information by a factor of 7, yes, what you would say?
I was going to say maybe the difference is that pixel information doesn't really matter in images, whereas with words, each word value matters a lot. You can't really reduce.
I'm not sure I understood. Okay, I think you start to get the intuition. Yes?
It's like, what was it? I was about to say that like in the pixel or in images, I totally forgot.
No worries. So I can reduce the amount of information by 7 times, by a factor of 7, and I can still have the same, I can recognize as a human the same class. So this means, okay, let's take the same example and say we have a text and we remove 70% of the information. Would we be able to understand the text? Probably not, right?
Probably not.
So the difference lies in the redundancy between the different signals. And if you go one step further in videos, the redundancy is even higher. So if you take, let's say, 20 frames per second, the redundancy between those frames is significantly larger. But we can already see that from a single, let's say, image. So if we have 15 masking ratio and we are able to reconstruct, at least we ask the network, this pretext task, to reconstruct the rest of the text. So in language, the intuition is that we need a large, it's more intuitive to use a larger, maybe significantly larger. We'll see the different approaches. Yes?
Okay, this masking, is it the redundancy or the future extraction is really not that much dependent on the pixel values like the text? In text, the future extraction is heavily dependent on tokens, but in this images...
It's still tokens. We're just talking about the tokens here are the patches. So the projection of the patches are the tokens of the sequence. So this would be, in vision, this would be patch 1, the projection of patch 1, the projection of patch 2, the projection of patch 3. I don't know if you remember with vision transformers that you have this input and you take these non-overlapping patches. So the intuition here is that we can mask a larger amount of information, because even with, let's say, 50% of the information of the image, we can still understand the object. All right. Nonetheless, they made like an extensive analysis. Either so the objective here is mean square error on the image space. So they make an extensive analysis to different masking ratios. Here you can see from 10% to 90%, and they made some graph, which is not a general conclusion that you should use for any method these ranges, so from 70 to 80%, you see it's like almost the optimal ranges. But this is like specifically to this approach, but you should expect that all different masking-based approaches that you will see in vision will have at least a larger amount of masking ratio. So here they found that the optimal is around 75 for natural languages. And for those who like this kind of different application fields, I used to train some models, some autoencoder vision transformers on microscope images, and we found out that this behavior is not the same when you have these populations of cells. You need a much smaller masking ratio. So the redundancy is smaller. And the additional results, if you can see on figure 8 on the right, that they still perform given that you fine-tune. So by fine-tuning, I don't know, for those, we'll make a significant distinction, we'll clarify and emphasize on the difference between probing. So do you remember from the exercise class what is probing? So you keep the representations fixed or frozen, and then you only train one single linear layer without a lot of bells and whistles on pigmentation and anything. And fine-tuning means that you train both the network that you pre-train, so it's like a random, it's like a different alternative to random initialization. You initialize with the weights you learn from the pretext tasks, and then you also train the backbone or the pre-trained network plus the classifier. So these results are on fine-tuning, and you see here there is a small discrepancy between those two approaches, so linear probing versus fine-tuning. We'll talk about that a lot today. And they can still have a better behavior than, so here we're not only interested on the y-axis, which is the validation accuracy, but we are interested on how much we can scale. So given that we have an infinite amount of compute, so GPUs in practice, how do different over-parameterized models scale with respect to the validation accuracy with respect to the number of parameters they have? Okay, the number of parameters is not by itself a comparison for the computational complexity for a specific architecture, but given that you have the same architecture, so BEiT-based, and you just change number of layers, number of heads, embedding dimension, only these three parameters, almost linearly scale up these three parameters, you can compare between the number of parameters. But if you had, for example, ResNets or different convolutional networks, the x-axis wouldn't make so much sense. That we have other metrics for that. So they still have, so the pre-training from the master encoder happens on ImageNet and the fine-tuning. So one might ask, is this network just memorizing the data? Like, can you memorize with a bigger model? Can you just memorize 1 million images and learn how to reconstruct them? And to answer this question, okay, and this is a pre-training, supervised pre-training on a huge private data set of 300 million images, which is still surpassing this approach. So to answer the question, if the model is just memorizing the data, we need to, one way to answer this question, at least visually, is to inspect the reconstructions of the validation data, so that the data that the model has not been trained with. So these are a couple of validation images from the same data set, so the same data distribution that the model is trained on. And we can see that the model can create plausible results, even though they may not always correspond to the real class. And you can perform inference with any number of masking ratios that you want. So you have maybe 75% for training, but they also show that you can have even a larger number of masking ratios during inference. So here we want to have an idea of how the model learns to reconstruct. So how well the model performs on the pretext task. But that maybe or maybe not will give us some indication of the performance on the downstream task as to whether it memorizes the data or not. So the question here is, why the results are so blurry? Do you remember?
Because of MSE.
Sorry?
Because of MSE.
Yes, because of the training objective. Because we saw that when you reconstruct the data with either L1 or L2 loss, but directly on the image space, the network generates blurry predictions. So you should definitely have learned this during this course. But we don't really mind at this point, because this is like a type of, let's say, generative pretext task, but we care about the intermediate representations learned from the encoder, because we want to use them to classify images. So another intuition here is that even though we mask patches, since we have unlabeled data, there is no indication that the patches that we mask randomly refer to different object entities that may correspond to the image semantics. So if we have...
Would you be able to repeat your last sentence?
Yes. So if we have an image with objects, so if we have an image with different semantic categories, so objects that we, let's say in the downstream task, we would like to recognize these objects, either with assigning a single label to each pixel, or just with learning bounding boxes for these different objects. When we just, let's see if I have another clue. So when we just randomly mask part of the information, so the red ones correspond to the random patches that we want to mask. There is no indication, as they write, that the removal of these random patches corresponds to a semantic segment. So in this example, we mask something that we want to reconstruct, and it would be useful to learn the intermediate representations that reconstructs this entity. But for example, these paths, we have no indication. It will not lead to a meaningful representation by reconstructing something that we don't really care for the downstream task. Is that a bit more clear at the moment? However, still, even though we have no prior knowledge that this random masking will be beneficial, the authors argue that you can still learn very rich hidden representations inside on the output of the encoder of the Fusion transformer. Okay, and maybe a last question, that just small small emphasis. So if we have like from 0 to 100% masking ratio, and here we have the complexity this would lead to, it will not be probably linear, but it will have this kind of behavior. So this is the complexity when you don't mask the image. So it's like the baseline complexity, just processing an image with a vision transformer. And this would be, let's say, 0 complexity. If you mask all the image, you have nothing to process on the encoder. And the more you mask the image, the more you reduce the complexity of the encoder. So this is the most attractive component of this architecture. Is that very, very clearly established? Okay. However, BERT doesn't work in exactly the same way.
Nico,
Yes?
how do you measure the complexity of the encoding? What's the method?
Yeah, so I will tell you the answer directly. So the best way to measure the complexity in practice is to establish some references. So you say given hardware, given a specific hardware, so let's say one GPU of a specific type and a specific batch size that fits for all the different models or for different setups of this model. And given a data set D, so let's say 100,000 images, you perform inference with, let's say, not just one, but a lot of those images. Let's say a data set of at least 10,000 of those images, and you measure the GPU time to process the images. So you measure images per second. So you measure in a given hardware with a given, I don't know, PyTorch CUDA version, how many images you can process in 1 second. There are other metrics which like the flops, floating point operations per second, but this is the most accurate one. So let's go to another approach, again borrowed from natural language, where we try to create a pretext task very similar to BERT. So the acronym is called BEiT. I don't remember what exactly it corresponds to. But the idea is slightly different. So now we are not directly relying on the image space. At least for the pretext task, but we try to assign its path to one specific entry in the vocabulary. So similar to natural language where we have like 20,000 words, here we have this notion of visual vocabulary. So we try to say, I also used the word overclustering in the previous lectures. So we're trying to say that no matter which and how different an image path can be, it has to be assigned in one of those 10,000 or 100,000 classes. So this is like a more discretized objective where we want to train with cross-entropy. But the question comes is that, okay, this begs the question, how can we assign image patches to discrete values in a set of visual vocabulary? So visual vocabulary or prototypes or codebook, different papers use different terminologies, but they all correspond to the same thing. We want for each patch to have one discretized class. And I don't know if you have already understood, but neural networks don't like discrete stuff, especially during the optimization. Nonetheless, they use So they use another task, let's say, before the pretext task, which aims to map the patches in a given discrete code book or visual vocabulary. And they do this by training an autoencoder. So this by itself is not enough, because you have an encoder, a decoder, it doesn't matter if it's a vision transformer or not. Any type of encoder and decoder, you still optimize both networks to reconstruct the image, but now we will not keep this representation for the downstream task. We will just infer some vocabulary. We'll try to map the latent space, which is a hidden, let's say, continuous space. So you have just a vector of continuous values, and we will try to map this latent space to a specific number of visual vocabulary. All right? So the question is how we do that. Because if we do that during the optimization, as it's on right now, it's not. Do you know why is there a problem if we discretize this latent space here? Do you have any intuition why this would not work? If we just find a way to discretize, any ideas? Let's see. Okay, no. Okay, it's a bit not very obvious. It's not so obvious. So when you optimize the mean square error, you cannot propagate the gradients here, because discretization is a non-differentiable operation. All right. So here we cannot just propagate the gradients and train the encoder. If let's say in the vanilla case where this is just a latent space and we apply some sort of discretization. So we need to solve another problem, how to discretize the latent space, which is the main difference between this BEiT version 1 and version 2. But let's say we do find a way to discretize the space and assign each image path to a specific visual vocabulary. Is it clear that then the pretext task is exactly the same as in BERT? Can somebody describe how the pretext task would look like based on the image, given that we solve the problem and we assign each path to a visual entry? Would somebody like to try to describe how this BERT approach would work? I don't know, maybe it's too obvious. You take the sequence, which is the projected patches, and then you mask the similar way you would mask words. You just have to pick a different masking ratio for the reasons we discussed, a larger masking ratio. This is just positional embedding, not so important for the method. You process this with a transformer encoder, and you just apply cross entropy for the masked tokens. Is this clear? If yes, let's see how we can discretize the space. So the two ways to discretize refer to BEiT version 1 and version 2. Here I want to emphasize that the discretization problem that leads to non-differentiable, so we cannot basically train a model like that. So the first version is a bit complicated. I haven't really checked all those papers, but these references. So they apply some mathematical approach, which is called Gumbel softmax relaxation. But the most, and this is probably what they got wrong, because then in the next version, so this BEiT version 2, this is the result of the first approach. We will see them later. Along with other things, but I want to emphasize that this is the way to learn, this is the state-of-the-art method backed with some theory on how to discretize the latent space and still keep everything, to still maintain that this process is differential. So you have these vectors, and you compute everything is L2 normalized as always, and you have some codebook embeddings. So codebook and visual vocabulary is the same thing. So we define some vectors that correspond to, okay, let's simplify. Let's say we have 10,000 classes, codebook classes, and for each class we have a vector of a specific dimension v. So k here refers to the 10,000, and then we just find for each individual token representation, we find the closest vectors. So these are learnable vectors, randomly initialized in the beginning, but still learnable during the training. And we find the vectors using cosine similarity. It's called nearest neighbors lookup, but it's basically cosine similarity because everything is L2 normalized. And we find the entries of the codebook that correspond to these 10,000 vectors and use those for the decoder. So that's why you see different colors here. So this is the untouched output of the encoder, and this is so the arrows here correspond. So each one of those representations of the tokens will be mapped to one of those trainable vectors and will be used on the decoder. And the gradients, since the shapes are the same, will be just copied. So it's a small trick, but I find this to be a very useful technique, and it's the state-of-the-art method to discretize the latent space in case you deal with problems in the future outside of this course, where you would desire something similar. Any question on how this approach works? Yes?
Can't we just like extract the features and then try to map them to a discrete like values without having to do all of this?
How would you map them? You have a
Like we do the training normally and we extract features that are not like discrete values, and then we map them to some discrete values that we can then feed to the BERT model.
So let's say we have a batch size of 1 and we take the outputs. What do you want to do with them? Like if you feed them directly, it would still be continuous values.
Yeah. After that, like when we extract the features, after we're done with the
After the decoder.
after we've done the whole training, we have some features, and then we can use like we can map those features to some discrete values.
To do like to train on the latent space and then try to discretize the latent space.
After we're done with training.
This is a simple baseline. I guess somebody must have tried it. I don't know as to whether it can work, but I know that this one is like the most theoretically justified method to create, because here the codebook, so these trainable embeddings are not word embeddings, so it's not like path embeddings or input embeddings, are like the prototypes, so vectors that will be learned alongside training, and they will be optimized for your specific training data and task. While the discretization is a general method that you would apply later. So it's like a non-learnable discretization, what you said, like the baseline, just discretize the outputs. And with this trick to copy the gradients back to the representations from the codebook embeddings, we can, this is the best way that I would like you all to remember as a reference for the future. But do you understand, or it's like not at all clear? Okay, I will just repeat one more time. Any question? Yes?
Codebook embeddings.
These are initially, in the beginning, randomly initialized vectors. So you do a forward pass from the vision transformer. You get n is the number of passes, d is the embedded dimension or d model. Then you do, if everything is L2 normalized, it's just a matrix multiplication. So basically similarity. So you see, for example, for this one, for this representation, which entry of the code book has the closest similarity, and you use this one. So here you see the different colors correspond to this entry. Yes?
Could you brightly explain why they have to be discrete?
The discretization lies in the fact that here,
I know where it comes from, but why do we need it?
because we want to assign each path to one class, one codebook entry for the pretext task that we said, like to train in a BERT-like fashion. So let's say we want to kind of mimic this idea of natural language, where we have this vocabulary and we try to translate this into vision. So this is what people try to do. They try to incorporate this idea of BERT, because we know that BERT works extremely well for natural language and proteins and all this stuff. And we try to find tricks to do that in vision. So this paper is called Vector Quantized Variational Autoencoder, or VAE. And I think it's a great approach, even though it's not directly applicable for all the things we see in representation learning. So one last time, we have the sequence, we mask, and then we predict the mask audience. Since we have the labels, let's say, we get these labels, which is like the visual vocabulary. So the second version, this BEiT number, okay, they tried also another thing. They emphasized that everything we saw before with DINO, that you have this discriminative task, where you take the classification token and then you try to match the cross entropy between the teacher and the student. They try to create this hybrid of combining this mask-based generative approach with DINO, which is more discriminative, which try to match the cross entropy. And this was the first step towards the state of the art, but in their approach, just by plainly combining these two objectives, didn't illustrate any significant improvement by itself. But we will see this in the later version. Here is a typical approach of transfer learning or training from scratch versus having an initialized network and then fine-tuning. So you see that